Alright. Hello Mustangs, this is Miss Cantwell, and I thought that I would go through some example problems from the homework so that you guys could have a resource outside of class to practice solving these problems. So this is for L or K. The first two problems I'm going to do are from the L worksheet, but K students can absolutely solve them if you need more practice. So the first problem says a toy car runs off the edge of the table that is 1.225 meters high. If the car lands 0.4 meters from the base of the table, how long did it take the car to fall, and how fast was the car moving across the table? So this is the way the problem read on the worksheet. I'm going to try to walk you through filling out the entire table so that anything that does come up, you feel like you've been able to do it. So the first thing we need to recognize is for L, all of your problems are just horizontally launched. For K students, we need to recognize there's no angle in this problem, so it is not a horizontally launched projectile. So that tells us right away that our horizontal acceleration is 0 meters per second squared, and that our vertical initial velocity is 0 meters per second, and our acceleration is negative 9.8 meters per second squared. You can put those values in right away if you know that it's horizontally launched. Then we can look at the problem for more information. So it says it runs off the edge of a table that is 1.225 meters high. Okay, if it says something like high, or talks about the height, or it talks about a cliff or something else that is generally tall, we can assume that that is going to be a vertical component, and because it's meters, we can say that it is a displacement. So we're going to go ahead and make it negative because we know that this toy car is going to be falling, and if it's falling, it's moving in the negative direction. Okay, if the car lands 0.400 meters from the base of the table, okay, anytime it says away or from the edge, we can assume, we can concur, that that is a horizontal value. And because it says meters again, we know it's a displacement. So we're going to put 0.400 meters in for our horizontal. So the first question that's asked is how long did it take the car to fall? And most often, that'll be the first thing that you'll need to solve for anyway, okay? So the proper way to do that is to recognize, okay, I don't have enough information on my horizontal side of my table to be able to find time here, okay? I do have enough information on the vertical side, so I can only use the information on the vertical side, and I can only use these equations. Of the equations that I have available to me, these two have a variable that I don't have, so I can't use them. So I'm going to use this one. So for part A, I'm going to say delta x is equal to vi delta t plus 1/2 a delta t squared. Okay, from our paper, we know that our delta x on the vertical side is negative 1.225 meters. And that's going to be equal to our initial velocity, which is 0 times our time, plus 1/2 of our acceleration, which is negative 9.8 times our time squared. Okay, the 0 delta t, 0 times anything is always going to be 0, so that term is going to drop out. So we're going to get negative 1.225 is equal to 1/2 of negative 9.8, which is negative 4.9 times delta t squared. Okay, then we have to get rid of the 4.9, and we have to do that by dividing, because right now it is stuck to that delta t. So the only way we can get rid of it is to divide it. Okay, so 1.225 divided by 4.9 is equal to 0.25, and that's going to give us delta t squared. Okay, so we're not finished. We will have to take the square root of 0.25. Okay, so the square root of 0.25 is 0.5 seconds for our delta t. Okay, so I'm going to go ahead, I don't know if you noticed, if you're in my class, you notice that I always write the vertical component and the horizontal component in separate colors because it helps me keep things separate for myself. If you want to do that, go ahead. Okay, if you're a visual person, it will definitely help. Okay, my time though, since it gets to go in both sections, I'm going to write in a color that I reserve for a resultant. So 0.5 seconds on both sides. Okay. Part B says, how fast was the car moving across the table? So here we're going to practice solving for a horizontal velocity. Okay. And because it's horizontal, we only are going to use the horizontal equation. Okay. So V is equal to delta X over delta T. We're looking for V. Our delta X is 0.400 and our time is 0.5. So 0.400 divided by 0.5 will give us 0.8 meters per second. And we can plug that into our initial horizontal velocity and our final horizontal velocity because the acceleration is 0, so we know the velocity is not changing. Okay, that's all that the problem asked us for, but you might also be asked to solve for the final vertical velocity. Now, you have enough information to use either equation 2 or equation 3 from the list up here. I'm going to solve it with equation 2 for this problem. The next time I'll solve it with equation 3. Okay? So equation 2 says A is equal to VF minus VI over delta T. A is negative 9.8 because we're using vertical information. We're looking for VF. VI is 0 meters per second, and our time is 0.5 seconds. So negative 9.8 times 0.5 gives us negative 4.9 meters per second for our final velocity. Okay, that was the problem from L worksheet 2, and it's problem 5. So even if you're in K, you can still access the L worksheet if you need extra practice. Now I'm going to go ahead and do problem 3, but I changed it just a little bit to make us solve for a couple of different variables. Okay, so again, this is going to be a horizontally launched problem, so I can fill in my horizontal acceleration of 0 meters per second squared, and my vertical initial velocity of 0 meters per second, because it's horizontally launched, my acceleration of negative 9 meters, or negative 9.8 meters per second squared. Sorry about that. Okay, so it says a dodgeball is kicked horizontally at 10 meters per second off of a cliff. Okay, the ball hits the earth below in 2.02 seconds. So it says it's kicked horizontally, and this meters per second tells me it's a velocity. So I'm going to put that here in my initial and final horizontal velocity spots. Okay. The 2.02 seconds is the time it was in the air, so I can put that in both spots, both the horizontal and vertical, because they share time. Okay. The first question says, how high was the cliff? So that would tell me that we're looking for our vertical displacement. So the only formula we have enough information to use is this first one. So delta X is equal to VI delta T plus 1/2 A delta T squared. We're looking for our displacement this time. So we can say our initial velocity times our time plus 1/2 of our acceleration times our time squared. Okay, so 0 times 2.2 again is going to be 0. 1/2 of negative 9.8 times 2.2 or 2.02 squared. And if we do that, it will give us negative 19.99 meters. So it's about 20 meters tall. Okay, so it gives us a negative displacement. So we can put that here. But if you're asked for height, you should report it as a positive number because height is scalar and does not have a direction associated with it. B says, how far away from the cliff did the ball land? So this tells me that we're looking for our horizontal velocity because it says how far away from the cliff. Okay, so for part B, we're going to use our horizontal information, and the formula V equals delta x over delta t. Okay, our velocity is 10 meters per second. We're looking for our displacement, and we have our time of 2.02. So this is where some of you guys maybe made a little mental error when we were doing the CFU. You have to make sure that you follow through with the algebra. So you're going to have to multiply both sides by 2.02 because we need to get it off the bottom over here. Okay, so 2.02 times 10 is 20.2 meters, and that's your displacement. Sorry, 20.2. So just think about when you're following through the algebra. Some people like to just try to divide everything or add the numbers together, but if you use the equation as a tool and follow through the algebra, you'll be just fine. Okay. Now I'm going to switch to some problems that were on the K worksheet. For this one, okay, Els, you guys can do most of this, so if you want to try to follow along, you can. All right, this is problem 6 from worksheet 2, which was a horizontally launched projectile worksheet. Okay, so before we start, since it's horizontally launched, we know that we can put 0 meters per second squared in for our horizontal acceleration, 0 meters per second for our y initial velocity, and negative 9.8 meters per second squared for our vertical acceleration. It says he takes a swan dive from a 13-meter board. He leaves the board at 6.5 meters per second. His initial velocity is horizontal. At what angle and what speed does Freddie hit the water? Okay, so this problem has a lot of parts to it. So first of all, we get the 13 meters. That's going to be our vertical displacement because it's talking about the height of the diving board. Then it says he leaves the board with 6.5 meters per second and it's horizontal. So we can put that for our initial horizontal velocity and our final horizontal velocity because, again, our acceleration is 0. So in order to determine his final resultant velocity, which would look something like this. Okay, this would be his resultant velocity. We would have a horizontal component, we call that Vx, and a vertical component, we call that Vy. Okay, in order to determine Vr, we need both of these things. So let's find, we do have enough information right away to find our vertical final velocity if we use the third equation. Okay, so A equals Vf squared minus Vi squared over 2 delta x. So negative 9.8 is equal to Vf squared minus 0 squared over 2 times negative 13. So 9.8 times 2 times 13 gives us 254.8, and that's equal to Vf squared. So we have to take the square root of both sides. And that gives us 15.96 meters per second. And it's actually going to be a negative velocity because he's moving downward. It just doesn't come out negative in the calculator because when you take the square root of a number, it could be either positive or negative. So you just have to add the negative if you know the object is going down. It doesn't really affect the math in this problem, but it's important to kind of think about that as we move on. Okay, so we know that our horizontal velocity is going to stay 6.5 meters per second. And we know that our vertical velocity final is now negative 15.96 meters per second. So in order to find the magnitude of the resultant, we're going to use Pythagorean theorem. Okay, that says that a squared plus b squared is equal to c squared. Okay, the short sides are a and b, so negative 15.96 squared plus 6.5 squared is going to equal our resultant velocity squared. Okay, usually when I plug this in the calculator, I do the square root of the entire thing. Okay, so 15.96 squared plus 6.5 squared is 296.9716. So I can just go ahead and take the square root of that, and I will get 17.23 meters per second as my resultant velocity. Okay. Now, in order to find the direction, we are always going to look at, for our level of physics, we're going to look at the angle that's relative to the horizontal. So that's this angle here. And it's going to be below the horizontal since the object's coming down. Okay, so this is where we bust out our trig. And really, you could use any of the inverse identities that you wanted to because we now have all three sides. It's completely up to you. I usually use tan. I don't know why, I must just like that one. So tan negative 1, and we need the opposite side of the angle, which is 15.96, over 6.5, which is the adjacent side. It's really important that you make sure that your calculator is in degree mode. If it's not, you'll get a funky answer, okay? And it's important to check because I know math makes you clear your calculator before and after a test. So every time you do that, though, you change back into radian mode. So you just need to kind of be aware of that. All right, so the inverse tan of this gives us a theta of 67.84 degrees, and that's going to be below the horizontal. So this problem didn't ask us to solve for time or for the horizontal displacement, okay? We've already practiced solving for those, though, so you guys should be okay doing that. Next one. This one is a non-horizontally launched projectile. So it's going to have some components that L students may not understand or want to listen to. So this one is a K-only problem. This is from, it's Worksheet 3, Problem 5. So what this one says is an arrow is shot at 30 degrees above the horizontal. It has a velocity of 49 meters per second. This velocity is going to be a resultant velocity, okay? So we're going to draw our resultant velocity, and we're going to say that it's 49 meters per second, and that the angle is 30 degrees. We can also say that we know that our vertical acceleration is negative 9.8 meters per second squared, and our horizontal acceleration is 0 meters per second squared. Okay? The horizontal component of this resultant is Vx. Okay? We can find Vx using cosine because it's adjacent to the angle. So cosine theta is equal to opposite over adjacent, or sorry, adjacent over hypotenuse. Okay? Which in this case, cosine of 30 is equal to Vx over our resultant, which is 49. So we're going to wind up saying 49 times the cosine of 30 will give us Vx, which will be 42.44 meters per second. And we can put that in for our initial horizontal velocity and our final horizontal velocity because we know that they are the same. Okay? Now, did the problem ask us to solve for the initial velocity component? No, it didn't. Okay? But we'll need it to figure out some of the other things that it's asking us to solve. Same with the vertical component. Vy is on the opposite side. So we're going to use sine theta is equal to opposite over hypotenuse. So in our case, it will be sine 30 is equal to Vy over 49, or 49 sine 30 is equal to Vy. So Vy is going to be 24.5 meters per second as its initial vertical velocity. Okay, now, when that arrow comes back down, okay, it'll reach a high point in its trajectory, and then it will come back down. And we're going to say that it has the same height at the bottom as it did when it was initially launched. Okay, so we can say that our final y velocity will be negative 24.5 meters per second as well. So we're looking at the whole trip here. The first question says, how high will the arrow go? So in order to figure that out, you need to think about what are the velocities here. Okay, so our initial y velocity is 24.5. Our final y velocity is negative 24.5. And its maximum height, the y velocity, is 0. Okay, so if we wanted to find the height, we could use this third equation and make either the final velocity 0 or the initial velocity 0. My preference is to do the final velocity. So I'm going to say A is equal to VF squared minus VI squared over 2 delta x. Negative 9.8 is equal to 0 squared minus 24.5 squared over 2 times delta x. Okay, so we will have negative 19.6 delta x is equal to negative 24.5 squared, which is 600.25, and we wind up dividing both sides by that negative 19.6, and we will get a delta x of 30.63 meters. Okay, so I always write max height in here because it's not the full vertical displacement of the arrow. That would be 0 meters because it starts at the same height that it ends with. Okay, B says, what horizontal distance will it travel? Well, in order to know the horizontal distance, we have to solve for the time. So I can use any of these equations that have time in them that I want to solve for the time. I like to use the second one and use both of these as my velocities. So A is equal to VF minus VI over delta t. Negative 9.8 is equal to negative 24.5 minus 24.5 over delta t. Negative 9.8 delta t is equal to negative 49. That was silly. We already did that. Divided by negative 9.8. And we get a delta t of 5 seconds. So this arrow was in the air for 5 seconds. So since that is for our entire trip, I can go ahead and put it in both columns. Now, I could have used the same formula and made one of these velocities 0, and I would have gotten 2.5, which is half the time. Okay, since we were solving for the horizontal distance, we need to use the horizontal velocity and this equation. So V is equal to delta x over delta t. 42.44 is equal to delta x over 5. You have to multiply both sides by 5. And you get 212.2 meters for the horizontal delta x. Okay. Hope this helps.